Yang-Shi is from Flinders University, and she'll be talking about normalizer theory of Coxeter groups and discrete integrable systems.
Good morning, everyone. Today I want to talk about an application of a recent or relatively recent theory in representation theory of normalizer theory of Coxeter groups, and in the context of discrete integrable systems. And this is based on a work from 2019. So the plan is that I'll first give a brief introduction of Coxeter groups and also the relevant discrete system in my talk. And then I'll explain why normalizer theory of Coxeter groups is relevant in this context. So Coxeter groups classified by Coxeter in 1935 is defined simply as a set of generators subject to the following very simple set of relations. And the generators are indexed by a something we call alpha I, and what they are will be explained shortly. In the context of discrete integrable system, we are mainly concerned with what is called the Weyl group, and that corresponds to this number Mij being 2, 3, 4, or 6, and which is also called the crystallographic condition. The classification of Weyl groups are given in the following types, and their affine extension are denoted by this subscript bracket 1. So Coxeter groups are known also as reflection groups because the generators can be realized as a reflection in a real vector space equipped with a bilinear form. So the formula of reflection on this space is given as follows, and it's the usual reflection formula for a real vector space. That is, we see that from the formula Si will take alpha I to negative alpha I, while fixing anything that is orthogonal to alpha I. So that is how a reflection is defined. So now the set of all the alpha i's is form a basis of this real vector space, and it's called the simple system. So I use this to refer to the different types of Weyl groups. Now, there is a graphical representation that concisely describe these group relations, and that is for Mj for taking value of 2, 3, 4, or 6. We have the following connection. The nodes corresponds to each generator of the group. So, and in the classification of Weyl groups, we have something called simply laced or non-simply laced, which are given here. We see that for types A, B, and the E types, connections are all single connections, whereas B, C, F, and G contains multiple bonds. Let's look at the example, since we talk about reflection of the type A2. So there's a lot of things going on. So let me explain one by one. The finite Weyl group is generated by S1, S2, corresponds to this part of the thinking diagram. Since the bond is a single bond, that means the product of S1 and S2 to 3 times is the identity. This is reflected here as the reflection plane for S1, the generator S1 and S2 has an angle of pi on 3, and the product then of S1 and S2 will be a reflection by twice of this angle, which is 2 pi on 3, and therefore apply 3 times, we'll have the E identity. We have the simple roots alpha 1 and alpha 2 corresponding to the 2 reflections, orthogonal to the reflection plane of S2 and S1. Now, the affine extension denoted by this S0 now make this the finite Weyl group of A2 into a infinite group, and the associated geometry goes from a symmetry of a hexagon to the hexagonal lattice. We can see here that the reflection plane corresponds to S0 is this one, and so with S1 and S2 and S0, we are able to go from a fundamental region of this hexagonal plane to anywhere using these 3 reflections. Moreover, with this affine extended thinking diagram, we see there is a thinking diagram automorphism, which we call rho, and it has order 3. If we extend the affine Weyl group by this thinking diagram automorphism, we use this tilt on top to denote we have an extended affine Weyl group. And in particular, the resulting group is the affine Weyl group semi-direct product with translations by what is called the fundamental weights of the Weyl group on the hexagonal lattice. So in particular, the element corresponds to this translation is given as follows. So it's a product of the generators of the following generators of the group. Here's the action of this element on the set of simple system, where delta denotes what is called the null root of the system. Okay. So discrete integrable systems are known since a long time. They arise as discretizations of integrable system, such as the discrete KP equation. And here already you see that they have corresponding Weyl symmetry. In the 2000s, there is a classification of lattice integrable equations called chord equations. However, those equations are known, all of them are known before. Some of them are known as the cross ratio equation or the lattice and KdV equation, which we heard about yesterday. Finally, we have a classification by Sakai of discrete Painleve equations, and they are listed as follows. So now we see that we have affine Weyl groups of types going from the E type, exceptional type, down all the way to the A type. The lower part of this cascade, we have the discrete symmetry of the 6 Painleve equations going from D4 type for the 6 Painleve to A0 for P1. So I will explain using the example of the 4th Painleve equation how the affine A2 symmetry arises. The 4th Painleve equation written in symmetric form is as follows. So it's a second order nonlinear ODE with some parameters. Nomi and Yamada give a birational realization of the extended affine Weyl group of type A2 for the 4th Painleve equation, and they are given in this table. So just to remind you, here are the relations satisfied by the generators of this group, and they commute with differentiation in this ODE. So to go back to the previous picture of the hexagonal lattice, that if we record that translation on this lattice by this much, or we call T1, is given by this element of the group, and using the birational representation on the F variables, we compute the following. And if we apply inverse of this element to F0, we get the following. And we see that this, given this definition, lead us to a second system of second order discrete equations. And on the lattice, we have the F variables associated to the edges, and F variables translated by this much is given by denoted as F1 bar, and this edge. So the advantage of giving a symmetry description of integrable system are many. For example, generalization to higher dimension is clear using symmetry by extending. Before we have a system of A2 times A1 type, and this can be taken into arbitrary M and N. This is given by Kajiwara, Nomi, and Yamada. The generalizations of P6, which will have default symmetries and its Q discrete analog, are given to arbitrary N. More recently, there is another generalization of the P6 equation with the following symmetry coming from a cluster algebra setting. Moreover, relations between different discrete equations are clearer. For example, the A-type KP equation, which is a discrete PDE, partial difference equation, is related to a discrete ODE, Q-Painleve equation, through symmetry. And similarly for different types of integrable systems. So we have found a relation by simple relation between the two symmetry groups relating the quad equation, which has hypercube symmetry, to an n-type Painleve equation. So what about the symmetries that are not listed in the class inside of the classification? Because if you look at Sakai's list, the symmetries listed there are the full symmetries of a surface associated to a particular surface. Unless by construction, systems, I would say, found in nature rarely have this full symmetry of the surface. And what we find is a given discrete evolution, that element is not a translational element of the affine Weyl group. However, some iterations is a translation. So to show you an example, it arises as orthogonally intersecting circle pattern investigated by Agafonov and Bobenko in the 2000s, and it is associated to the P6 equation with default symmetry. So two orthogonally intersecting circle has 4 points of interest. 2 are the centers of the circle, 2 are the points of intersection. If they are orthogonally intersecting, then the location of 4 points satisfy the following cross ratio equation. If you want to extend this circle orthogonally intersecting circle pattern throughout the plane, then Niehoff, Romani, Grammaticos, and Otta found that the following 5-point relation on top of this cross ratio equation. So this 5-point equation basically give you the correct boundary conditions such that you are able to then continue this circle pattern along the plane. And in particular, they found that the compatibility of these two equations is related to the P6 equation. In 2017, we found that the symmetry of this particular system does not have the full symmetry of P6, but it's given by the following type of subgroup subsystem of D4. In particular, the element that is associated with translation, creating translations along this direction, which we call row 1 and row 2 here. Yeah, they are not translations of the symmetry group of P6. However, iterated twice, they are translational elements of the default group. So how to explain such subsystem within the integrable system we have? So similar situation have been found earlier. For example, in the KNY's system of type A3 times A1, Takanawa has found the embedding of this system as a subsystem of Sakai's D5 Q-P6 equation. The example of circle patterns And more recently, there has been a equation with F4 symmetry, that is a non-simply laced type subsystem found by Atkinson, Howe, Joshi, and Nakazuna as a subsystem of Sakai's elliptic E8. We found so far that all these systems, the subgroups can be explained using the normalizer theory of Coxeter groups. I've kept Coxeter groups rather than Weyl groups because the theory is general to Coxeter groups, not only just Weyl groups. However, Weyl groups is what is relevant for us at the moment. So given a group and its subgroup, the normalizer of this subgroup in the original group is defined as follows. When the W is a Coxeter group, however, and this subgroup is a parabolic subgroup, then the normalizer found by Howlett for finite Coxeter groups in the 80s and together with Brink in 99 for general Coxeter groups, that the normalizer decomposes in this case into what is the parabolic subgroup, semi-direct product of the parabolic subgroup, and what is we call NJ, or the complement of the parabolic subgroup in the normalizer. In particular, this NJ has the property that it's all the element of the group that act on J, this subset, commutatively. That is, it fixes this subset J setwise. So to understand this theory, we need to look at some basic properties of the Coxeter group. So let's define a root system of the Weyl group. We have it's defined as the set that we get by acting on the simple system, the group we have. In particular, it decomposes into positive and negative root system. And given this, so the positive root system is a non-negative combination of the simple roots. Then we can define the concept of length of an element of the group. So we illustrate this with an example. For the Weyl group of type B2, which is a symmetry of a group of for a square, we have two generators satisfying the following relations. Given a element, which we write as S2 as 1, we always read the element from right to left by convention, not because I'm Chinese. We see that this element can equivalently be written in this way. This follows from the relation, this relation. So these two elements are the same elements. However, this is the shortest representation of this element of the group, and the length of this element is 2. Then for finite Weyl groups, we have the concept of longest element. Its properties been proved in the Howlett paper. So I just state the fact. So this longest element is a unique element which is an involution, and its length is given by the size of the positive root system. In particular, it will act on the simple roots in the following way. So it will take a simple root to another negative simple root. And these longest elements act to different Weyl groups in the way stated here. So let's look at an example. For type of A3, so we have 3 nodes, and we see that the thinking diagram has a symmetry of order 2. The root system the positive root system has 6 elements. So this longest element has length 6. This is one way of writing it. And this is the action of this element on the simple roots. Oops, this needs to be alpha 1. So it takes alpha 1 to minus alpha 3, and alpha 3 to minus alpha 1, alpha 2 to minus alpha 2. So in Howlett's normalizer theory of Coxeter groups, we have something called movers and shakers, and they're denoted as follows. So given 2 subsets of the simple system, we can define the V element as follows. So you see it's defined using the longest element of the subsystem L and J. And this element, when we're choosing this I to be a single element set, it is called a mover if it acts on the set J, takes the set J to another set K. It's called a shaker if it permutes the set J. And what we're interested in, this subgroup Nj, are generated by these V elements, which are involutions. And they are also called R elements in Howlett's paper. They imply the fact they are almost reflections. So the group Nj is generated by these R elements. So I give an example of a shaker. Again, for the type A3 group. So we choose a parabolic subgroup system of 1, 3. And the single element subset, then I would be alpha 2. Together we have a system of type A3. The parabolic subgroup is of type 2A1, and its longest element then is given by the product S1 times S3. Then given by this definition, we see that this V element is given by S2, 1, 3, 2 by comparing these 2 expressions. And it is a shaker because it exchanges the roots 1 and 3. So a mover, again, using the same subgroups, is same type. If we choose a parabolic subgroup of generated by S1 and S2, then we have a parabolic subgroup of type A2. Its longest element is of length 3. We can write it as S212. And again, put into this formula using the expressions for the longest element of type A2 and A3. and compare, we get that this B element is S3 to 1. It acts on the simple system by taking 1, 2, 2, 2, 3, and it's for the mover. So for the rest of the time, I want to give an example, actually a computation of normalizer of Coxeter groups using Magma. And it's implemented by Howlett and Don Taylor since the 2018. So the example I want to look at is for a affine Weyl group of E7 type, to look at a normalizer of a parabolic subgroup of type A2 times A1. So the formula tells us that the normalizer is given by the following, where the parabolic subgroup is of this type. So this NJ is what we're interested in. This is the command that you type in Magma. So you first call up the Coxeter graph, which is already in the Magma system. It will give you something like this. So, and we make a groupoid by choosing the subsystem of 2, 3, 1. And this is a A2 times A1 subsystem. So what is a groupoid? Groupoid is a graph whose nodes are all these A2 times A1 subsets of this graph, and their connections are the elements that moves one subset to another. So for example, if we have this one, then another A2 times A1 subset will be this one, for example. So it's not too hard to work out all the A2 times A1 type subset of this graph and connections. However, it's very hard to draw. So this is a first attempt of drawing the groupoid. In Magma, you can ask if you type graph, it will give you the connection of this groupoid, and then using what is called a universal graph viewer, then you can draw this groupoid for this particular case. And so we see that we have 28 different subset A2 plus A1 type subsets in the E71 system, and their connections are given as follows. I have 3 minutes left.
4 minutes.
Okay.
Yeah.
So just to illustrate, for example, if we start with the subset 1, 2, 3 here, then to move to a different subset 2, which is 1 to 4, 1 to 4, we use the following V element. And if we want to move, say, to this one, which we see is 2, 4, 8, 2, 4, 8, we use this element. So the next command that you put into Magma to compute the normalizer is the following. After you've had your groupoid, And it tells you that it has 71 generators and 127 relations. It simplifies it, and it tells you it simplifies to 4 generators and 11 defining relations. Where does the 71 generators come from? Those are the shakers defined by this, and these are I've drawn them as these sticking out at the nodes. So there are together 71 of them, and you need to use the 127 relations to simplify them. However, Magma can do it for you. And in the end, we have a subgroup with 4 generators. And if you look at the 11 relations, it tells you it's a affine A3 type group. So the normalizer of this particular type of parabolic subgroup is given as follows. So this arises as recent work with Groupoids, Joshi, and Yale on a discrete non-system. And fortunately, when we first started looking at normalizer theory, the problem of F4 in E8 was much simpler. It arises as a parabolic subgroup of 4A1 type. So the normalizer of this subgroup, you see that it's simple because the groupoid is a single element. It's not a huge graph where you need to consider lots of generators and relations. The reason being, by choosing these 4 nodes, you're sort of stuck. There's no movers that moves this 4 to another A4 one subset. Generators of this NJ is given as follows, and they satisfy this F4 relation. So there are many ways of obtaining subgroups of Coxeter groups, for example, by folding. However, using the normalizer theory, the subgroups we get, we can realize it. Since they are generated by what is called almost reflections, we can realize them as reflection groups in some special subspace, and that looks like is the reason why they appear in discrete integrable systems. Thank you.
Thank you very much, Yang, for the very nice talk. Do we have any questions or comments?
You talked about the F4 subgroup and some direct sums of A-type groups. Have you found any other types of normalizer subgroups?
Yeah, lots. Because now Magma can do the job. At least you can first check what type they are.
Right.
To understand how to write the generator in terms of the original group generator, some work needs to be done, but at least you can check the types.
Yeah, that sounds great. That sounds fantastic. So perhaps we all need a tutorial in how to do this in Magma.
Is this a step towards a complete classification of these normalizing subgroups? Does that classification exist, or?
So in the original work of Howlett, in here there is a complete list, or almost complete list. Bob missed one case for E7, but in here a complete list is given for finite Weyl groups. That is possible. So at least there you get a sense of what type of subgroup is possible. But for affine groups and different Coxeter groups, I don't think you can list all of them. I guess, yeah, because there are many, right?
Yeah, yeah.
So I have a question. So So as you know, the translations, they correspond to Schlesinger transformations for the linear problem. And this gives you a lag spare for that direction and time. Do you know what's happening for these quasi-translations?
Yeah, I think this type of transformations was first found by Kajiwara and Nakazodo and Suda. So instead of translating this way, which is a translation on the hexagonal letters, the type of quasi-translation, we'll call it, actually moves like this on the letters. So you see that they are elements of infinite order, and they are not translations. But if you project that on that line, then it looks like this, looks like a translation there.
Yeah.
So it's a translation in a sub letters.
Yeah. That makes sense.
So the normalizer theory allows you to also find this subspace.
Yeah. Thank you. We have a question by Vladimir Majanov.
Is it possible to calculate in a closed for the action on the solutions? What is a closed?
Closed form, I guess.
Calculate action. Yeah, everything is explicit. So for example, here are the elements of the group, and this is a function. You compute this given by this table. You apply this from right to left, and the computation is closed. So for example, S2 satisfy this relation as a group element, but S2 F1 must give F1.
I'd like to thank you again, Yang, for the nice talk.
Thank you.